Great, and thank you everyone for joining. Thank you, Michael, for giving a great presentation. Kicks off a lot of the great background, good material of what I'm going to now build on, and I think a lot of the topics that Michael brought up as future needs, future research, I will try to elaborate on. I think the reliability versus resiliency question, that's a really good segue into some of this material, and really I think a good question to ask all three of the presenters here. I think if you ask three of us the same question, you'll get 4 or 5 different answers on that, because it is one that I think we think a lot about in the industry, but nobody has really a good, clear definition of the two. But so I want to build on what Michael just spoke about and really talk about how the resource adequacy topics, the modeling, the metrics, and the way we plan for a reliable system is transitioning now that we're moving to a system not only characterized by more renewables, but also by more energy limited resources like energy storage and demand response. So certainly with that transition, we need to transition the way we think about reliability. We need to transition the way we model these systems. And so first, I'd like to acknowledge Ecig. So they've set up a redefining resource adequacy task force that I'm leading with a broad group of other folks in the industry to really think about how best practices in resource adequacy planning should evolve as the resource mix transitions. And really a lot of the work I'm going to present today is an outcome of that. I'm just one voice of the many folks who provided some valuable input into that process. I listed several here, but there's others that go with that. So what I wanted to cover today, first, lessons learned from the California and Texas events. I think it's very near-term events here, and I think really valuable for framing the resource adequacy discussion, how this is evolving right before our eyes, and some real specific things we need to think about and what we can learn from those events. And then you can see I like my lists, obviously. So I'm going to talk about 2 driving factors, really the core reason we need to think about, rethink about resource adequacy. 6 first principles for resource adequacy. The idea here, what are 6 things that really underpin or should underpin any new way we think about resource adequacy moving forward? And finally, 4 recommendations for improved resource adequacy metrics. So I think Michael gave a great overview of the different metrics. There's a lot of them. I'll try to simplify some of that, but really think about how we can use those metrics a little better. And really, the objective of this presentation, I'm not going to stand here and pretend I have all the answers. What my goal is, especially to speaking to this group, this forum of regulators and policymakers, is give you some of the information or share with you some of the information that can just help ask better questions. I think that's really where we are in the industry. I think Michael showed that illustration of the railroad tracks. I think there's the modeling community and ways we can evaluate resource adequacy, and then there's ways we can implement that and how we can make decisions from that. And really, I think the most important piece of that dynamic is making sure both sides can ask the right questions on how the analysis was done, but also how decisions are being made based off that information. So again, quickly wanted to start this off with a recap of what happened in California back over the summer and what happened in Texas just recently in February. Both made the headlines for sure. Obviously, the most recent one in Texas was much bigger in magnitude, I think made even more headlines, but both of them are really important to see how resource adequacy analysis needs to really transform as the resource mix changes. So I'll start with California. That one occurred first. And I think looking at some of the fallout from this event, and I'll get into exactly what happened in a second, but Steve Berberich, the CEO of CAISO at the time, I thought framed this transformation or this transition of reliability analysis really well. And he said, there doesn't have to be a trade-off between reliability and decarbonization goals. And what caused the blackouts was just a lack of putting the pieces together. and we have to rethink the old ways of doing things. And I really, that quote really resonates with me. You know, as with both the California and the Texas events, there was a lot of finger pointing on all sides of those emergencies on who caused it, who's at fault. And I think what's really important here from a planner's perspective is that we can figure out ways that we can capture these events better and prepare for them a little better, not necessarily point fingers, but learn from them and adapt the way we redesign and change our resource adequacy analysis. So what happened in California? You probably remember, so this was an event back last summer, end of the summer, and it was really record-breaking temperatures across the West. And what's really important in that is a few things. One was that it was a regional heat wave. This was something, I have the figure there from the Weather Channel. It was across the entire Western US. So that entire interconnected grid, everybody was essentially facing similar challenges at the same time. And so Michael spoke a lot about transmission and the value of transmission from one region to another. I think one of the reasons this event caught the system off guard was because it was a regional event. And so we have to think about how we capture that from a planning perspective. The second is, if you look at the temperature data of that period in August versus the last 30 years, this was really a 1 in 30 year event. So the highest temperatures that California had seen in 30 years. There's two things that we should think about in that. One is, do we plan as system planners for a 1 in 30 year event? You know, Michael presented that there's a trade-off between reliability and cost, and reliability doesn't come free. And frankly, we don't prepare for, or we don't plan to be able to cover a 1 in 30 year event. But the second way to look at that is, while it's a 1 in 30 year event, is there an underlying trend in the temperature data? And I think the way we as an industry need to think about climate change and the reliance on historical data to frame our planning for the future, we need to be very careful about extrapolating historical trends in the weather data. So specifically what happened in California, you can see August 14th, it was actually two events that occurred on back-to-back days. I have a plot here of California's generation mix for August 14th. And what's really critical here is when the unserved energy, when the load shedding occurred. And it was in the evening period. I don't have the time slice on here, but on this one over here, you can see it started basically at 7 p.m. was the load shed. What's very notable about that is it's actually well after the gross peak load and occurred on what Michael referred to and other folks referred to as the net peak. So after netting out the renewables. Now, resource adequacy in California, the modeling, the planning reserve margin, basically what you plan for, is off of the system gross peak. And so essentially reliability planning is looking and saying, my highest load occurs at 5 p.m. I'm going to plan my system to cover me around 5 p.m. But what you can see is that the actual load shortfall occurred later in the evening. Load was much lower, but the resources that were available during that time, as solar started to drop off, as other resources became unavailable, that was actually the peak risk. And you're starting to see this regardless of where you are in the country, whether it's solar centric regions, wind centric regions, and so on and so forth, is peak risk of when you're most likely to have a shortfall event is starting to shift away from the peak load periods. It used to be kind of conventional way of looking at things was if we could cover the system peak load, we could cover the rest of the year. So we only had to focus on those peak load events. And we're starting to see that shift. It's starting to shift by time of day. It's starting to shift seasonally. Part of that's renewables. Part of it is the natural gas infrastructure. Part of it is the load shape starting to change. So, if you can take away one thing from this event, and really the ERCOT one as well, is there's no longer necessarily a one-to-one relationship between peak load and peak risk of a reliability event. Another important thing to think about with the California event, and we'll compare this with Texas is, could this have been predicted? And it's a great question. The reality is it was predicted. It was predicted quite well. So if you look at the California Summer Load and Resource Assessment from CAISO that was released in May, so every year they look forward at that summer peak period and say, what does my reliability look like for this coming summer? Are we prepared? What are the potential pitfalls? And you can see this one excerpt, again, three or 4 months ahead of the actual event, hit the nail on the head. It was lower imports were, they basically said the system is prepared, but the one place they could get caught is when there's a period with lower levels of imports assumed, specifically late in the summer when the hydro resources were more depleted, later in the day when solar generation dropped to zero, and specifically when a heat wave occurred that affected a broader area than just California. That's what could be the event. So the reality is this type of event, while everybody doing the analysis said 2021 is when we're looking at reliability or resource adequacy shortfalls, this event was very predictable. And in reality, if you look at the resource adequacy analysis, it's all probabilistic. So Michael went through all the probabilistic analysis we do, and we say, on average, 1 day in 10 years, the system is designed to have a shortfall, so 0.1 days per year. Now, that means there are going to be some years where things line up and we have shortfalls. So by definition, the way we do the resource adequacy analysis is specifically expecting events like this to occur. So I think this is a clear example that the analysis picked up on this risk, but the system was still short. So what can we learn from that? I think I just went over quite a few things. Solar and wind output was over 10 gigawatts during the peak load of the year. So that's really showing there is a lot of capacity value that was provided by solar and wind. If those resources weren't there, things would have been much, much worse. And so I think ELCC, effective load carrying capability that Michael went over, it's showing that on average, those resources are providing some reliability, but we can't use that in isolation. So a good way to kind of value the resources for the provision of services they provided in the middle of the day, but not necessarily something we can rely on in isolation for planning. The second one is really around this planning reserve margin and just knowing the time of risk. So planning reserve margin in California and most other places is specifically 115% of the system gross peak. But again, that's not necessarily the period of most risk. And so really the way I would kind of encapsulate this is a lot of people are quick to point the finger at solar and this being a renewables problem. I kind of take a step back and say, well, we all know solar is dropping off at 8 p.m. at night in California. So really, is that a solar problem or is that a planning problem? And again, not putting those pieces together. And then Texas, I just have one slide on this, but really, I think two really valuable case studies because the events were so different. So the summer California event, that was one that was, again, when we look at it in context, it was between 60 and 90 minutes across 2 days. 2 to 3% of system load was affected. It was able to roll across the system. So, while it was 90 minutes long, a lot of customers, it rolled through the system. So no customers were impacted for a huge duration. Contrast that with the Texas event, where we're looking at 3 to 4 days of rolling blackouts at a scale really that we've never seen before. 20, 30, even 40% of system load potentially at times. And really this was in the winter when ERCOT, again, historically a summer peaking system. You can see peak load nowhere, still lower than what it would have been in the summer. So if you just looked at this from a reserve margin perspective, sure, the system should have been able to get through that event. But obviously catastrophic failure. And the reason for that, extreme weather events is a correlated outage. So when Michael showed the coin flip example, and basically on generators going on outage, we say each generator, whether it's coal, gas, wind, solar, whatever it is, has a probability of being on forced outage. That's not necessarily uncorrelated. And so traditional or historic resource adequacy analysis said, sure, these generators will all fail and they will fail randomly. So if one generator is on outage 5% of the time, the chances of it lining up with another generator's 5% outage rate is very low. And when you do that across hundreds of generators, you say, oh, my risk of losing a lot of these in succession is low if they really are uncorrelated. And what you can really see here is whether whether it's impacting wind or gas or coal, is correlating these outages. And so it's not necessarily fair to say that these outages occur randomly. And I think that's really something that as an industry, we need to do a better job at in terms of resource adequacy analysis. So I'll segue from that. Again, I think two valuable case studies that get into some of these key drivers taking place in the industry right now. So I wanted to look at what are two key drivers requiring a change in the way we think about resource adequacy. One is chronological grid operations. And so here specifically looking at variable renewable energy, wind and solar that fluctuate from hour to hour. Energy limited resources, so storage, demand response, the availability of those resources in 1 hour really depend on what happened in the previous hours and what's going to happen in the future hours. And so now, not only do you have to look at every hour of the year in the example of variable renewables, but you have to do that in a chronological manner and see, from 1 hour into the next, how is the system actually going to operate? How are these resources going to be available? And that's a fundamental shift in the way resource adequacy analysis was done. If you look back historically, a lot of the resource adequacy analysis just looked at the system peak load hours and said, well, if I can cover my peak load, chances are I can cover the rest of the year. And I think historically, maybe that was okay to look at it that way, because if you really did have random generator outages occurring and you didn't have fluctuating reliance on weather, maybe that was okay. But now we're starting to see an increase as we start to rely more on variable renewables and energy limited resources. We really need to switch to not only evaluating every hour of the year, but also showing how the system will actually step from 1 hour to the other. So for the modelers on the call, I think this is where you're starting to see a blend of production cost modeling and resource adequacy into kind of a stochastic Monte Carlo analysis where you're running a production cost model hundreds or thousands of times with different weather profiles, different outages, and actually sequentially going through an entire year of operation. There's other drivers for the chronology there. One is hybrids. I think this is interesting because as you start to have resources that are combining different renewables, combining different fuel sources, and combining different amounts of storage, it really depends. Their availability now is a function of the weather, but it's also a function on how the operator plans on using that asset. And so there might be competing objectives of different resource types and things like that. And then lastly, flexibility, load flexibility. We always, as system planners in the past, always looked at reliability analysis as, do we have enough generation resources to meet a fixed load? And fundamentally, that is changing before our eyes. We are getting a lot more control on the demand side, and it's a valuable tool. So now I always try to be very careful with my terminology, although I slip up as well. Resource adequacy is really determining, are there enough resources available to serve the demand that we need? And so resources is really a combination of generation, of load, and of storage that can be both, and to meet the customer needs. The second key driver is correlated events. I talked about this a lot in the California, or in the ERCOT example. And I don't think this is new. I think the ERCOT event, had it happened 10 years ago, 20 years ago, I think we would have been in a very similar spot. So that isn't as much of a function of the changing resource mix. It's just from a planning perspective, in resource adequacy analysis, we always assume that these outages are uncorrelated. But in reality, these events are really due to correlation, oftentimes correlation because of the weather. So the weather really underpins everything. Michael, I think, had a really good example of this, or discussion of this. So it's the renewables are affected. So the wind and the solar are affected by weather. The load is affected by weather. And then the fossil generation also very much affected by the weather. I think that was very clear in the Texas design. And so what happens is, when before we look at wind and solar as having its random fluctuations and generator outages having random fluctuations, the reality is these things are all driven by similar events and correlated together. And so events can be the worst case scenario of renewables, load, and generator outages being a confluence of events. And I think just as an industry, we need to do a better job at thinking of how we can model that correlation. And then lastly, another item on the correlated events is we're shifting now to modular technology. And I think if you look back historically at the way we looked at resource adequacy analysis, it was, we were very focused on the probability of having large generators go on outage simultaneously to one another. And so if you have a really large coal plant, if you have a really large nuclear plant, what's the probability you lose a few discrete blocks of power at the same time? Because of an equipment failure. As we shift to more demand response, wind, solar, storage, all these are modular technologies. So even if there's a failure because of the equipment, it's only going to take out one of the inverters or one of a single wind turbine. It's not going to take out necessarily a full 1,000 megawatts at once. And so for that reason, again, we're shifting a focus away from those random outages and the random outage jobs and shifting focus, or should be shifting focus, more towards correlated events. And so those two drivers, chronological grid operations and correlated events, those are the two drivers that I think are fundamentally changing the way we need to think about resource adequacy. Again, neither of those are necessarily new. I think those have always been with us. I think just they're becoming increasingly important. So this is another way to look at that. And again, just a schematic here coming from NSOE in Europe. I think here it's resource adequacy analysis is essentially measuring the amount of available generation on the left, while taking into account all the uncertainty in wind, solar, and hydro, as well as forced outages of all of the equipment. On the right, uncertainty in temperature, and those are going to change every hour of the year. And there's going to be correlation on both sides of that. And then storage obviously can be a load or a generator. And it's really about finding how many times does one side of that scale tip the other direction when there's more load than available generation. Fundamentally, that's what resource adequacy analysis is doing. It's just counting the number of times the system is inadequate and you have more load than you have available resources. Again, have to be careful with some of my terminology because I do want to avoid available generation and kind of switch that terminology to available resources. So the Ecig work, collectively, this Ecig task force on resource adequacy, we got several folks together and thought about, how can we rethink the way we're looking at resource adequacy? If we were to start from a blank canvas, what are some of the first principles that we could continue moving forward, no matter what the resource adequacy framework was in a certain region? What are some of these first principles that really applied no matter what? And so the objective is to really articulate some of these evolving concepts to regulators, policymakers, and try to make that bridge between the folks doing the modeling and the folks making decisions from those model outputs. And so here's the result. I'm going to go into each one of these in more detail, but 6 first principles for resource adequacy. One is quantifying the size, frequency, and duration of outages is critical to finding the right solution. 2, there's no such thing as perfect capacity. 3, modeling chronological operations is essential. 4, load participation fundamentally changes the resource adequacy construct. 5 is neighboring grids and transmission are a key part of the resource adequacy challenge. And lastly, reliability criterion should not be arbitrary, but really make sure it's transparent, it's economic, and people know where it's coming from and how much it's costing. So I'll dive into each one of those in a little bit more detail. The first, this is just, and really wanted to clearly show, I know I'll be the first one to say, when I first got into resource adequacy modeling and analysis, all of the different metrics, the alphabet soup of metrics in RA was very confusing, or it was daunting to me before I got into it. And so there's probably several folks joining this where you see these metrics a lot, you don't really know what they mean or how to compare them. And I think what's really critical when you think about these metrics is you need to be sure you have a way to quantify size, frequency, and duration of when we don't have enough resources to serve load, how much are we short by? And loss of load expectation, as Michael said, it kind of the ubiquitous reliability criterion across North America, that is counting the number of events that are likely or could occur in a given year. And it does a very poor job. It's just purely counting the number of events. It does a very poor job telling you how big those events are. It's just saying, if I reran the same simulation 100 times, maybe 4 times I get 4 days across all of those years of simulation, 4 days where I don't have enough resources to serve load. Doesn't tell you how much you miss by, and doesn't tell you how much of any given resource you need. And so here I have a couple examples. The one on the left really just tried to make it straightforward. The blocks represent a certain amount of unserved energy. And you can see in this column on the left, both of these events have very similar metrics. So they're both one event. So LOLEV for this example, there's one event on the top, one event on the bottom, because these are contiguous hours where there's a shortfall. They also share the same LOLH, so loss of load hours. They're both 4 hours in duration here. So again, from an LOLE perspective, the loss of load hours perspective, these are identical events. You cannot distinguish them. But you see expected unserved energy, that's quantifying the amount of energy lost or unserved during that time. And you can clearly see that one at the top is a much larger event. So certainly some benefits to using EUE in that concept, or in that context. Second example over here on the right, again, 2 very different events, but sometimes the metrics can be confusing. So from an EUE perspective, we the amount of unserved energy in the 2 examples was consistent, but the number of events on the top, there's 3 disparate events. They occurred, there was time in between where you weren't serving energy, but the loss of load hours are the same. So you just have to be careful when you're interpreting metrics, understanding what's the metric, what's not. And the way I take a step back from this and say, really make sure you're using more than one metric, because all of them have pros and cons. And so where does this get to be important? We ran some analysis. Again, this is on a dummy system that was representing weather conditions in the southwest of the United States. And we ran 3 scenarios with different levels of wind, solar, storage, very different and disparate resource mixes. And we intentionally drove each of those to have the same LOLE. So all of these scenarios were a very different resource mix. All of them had the same LOLE of 1 day in 10 years. So technically, all of these are reliable if you're using a 1 day in 10 years. But then we plotted each of the events in isolation. So when you had an event where you couldn't serve load across hundreds and hundreds of years of simulation, plot that on a chart. And so we looked at that. On the x-axis here is duration of the event in hours. The y-axis is the size of the event. And then you can see at the top is a histogram of the frequency of events. So basically, of all the events, how many occurred that were 2 hours or less, 4 hours or less, and so on. And I like this chart because you'll hear me talk about this a lot, how we need to know about the size, frequency, and duration of these shortfalls. Well, this is one chart that can show you across the different resource mixes what the size, frequency, duration of the outages are. And as you can see here on the left, almost all the events were 2 hours or less. Over on the right, the same number of points, so the LOLE again is exactly the same between these cases, the same number of outage events, but you can see a much wider spread. You have some that are very long in duration, and much larger in impact, and some that are small. Now, these are very rare events. They might have only happened 2 times out of 400 years of simulation, but we are seeing a trend in different size and duration, even if the frequency is the same. So it's, again, critical that we have the capability in the modeling to look at what the events look like, but also from a decision-making perspective, know what we're looking at. Because what's critical here is the mitigations or the resource that you could add here might be very different than what's available here. Certainly if you had a 1 hour resource that you could call on frequently, that would get rid of nearly all of your events. So something like demand response would be an ideal candidate here, but when you move over to events that are 8 hours in duration and 700 megawatts in size, maybe you need a different resource. And so having this insight is really critical. Second principle is there's no such thing as perfect capacity. And I think this is a bias that we just fall into in the industry a lot, and kind of everybody's guilty of this. I find myself guilty of it quite often, where I'll say we need firm capacity, and you'll hear that term thrown out a lot. I really do my best to avoid using the word firm, and the reason for that is nothing's firm. If you look at the ERCOT example, which I'll get to on the next slide, you had outages just across the different fuel types. Nobody was firm in that event. And here, I think what we can learn from a modeling perspective is oftentimes we'll use the expected outage rate of a certain resource, so the average outage rate. And you can see that's what I have here at the bottom for, this is, I believe, gas resources, or sorry, this is all resources. So on average in Texas, the outage, 10% of the capacity will be on outage. But you can see during certain events, like the February event, we had up to 45% on outage. So there's nothing that's necessarily firm. Some resources might have lower outages and more availability than others, but really want to drive home the point that there is no perfect capacity. And so I think that, again, the trap we fall into is, for reliability purposes, let's go build gas turbines because that's firm. I think we need to rethink that and really put all these resources on a level playing field. And again, this is the ERCOT example. This is some nice work done out of EPRI I wanted to highlight. It really shows for the few days of the ERCOT event where each resource was relative to their SARA capacity. So seasonal assessment of resource adequacy, ERCOT's resource adequacy analysis. They say, natural gas out of the 70, 65 gigawatts of capacity, they count for reliability purposes to have a little over 50. You can see where gas actually showed up over the course of that week, 55%. And just go down the list, again, everybody guilty of kind of falling short. So again, no perfect resource. There's no such thing as firm capacity. And again, with the no such thing as perfect capacity, Michael discussed ELCC as a really good way, and I think it is a good approach to say for any given resources, what is its effective load carrying capability. I think where we have to be careful about that, one, if we're doing ELCC for wind and solar resources, we should also be sure to use ELCC to account for other resources. You don't want to mix and match and use partial capacity for some resources and assume full capacity for others. But also that these are very interrelated. I think I don't want to touch on it too much. Michael discussed this. This is, sorry, I should have a citation here. So this is out of E3, some of the work they did looking at portfolio effects, where if you looked at the capacity value of solar by itself and storage by itself, you get one number. But if you look at them together, One is trimming the peak and allowing the storage to have more capacity accreditation. So I think really important to know that ELCC definitely a step in the right direction for giving resources credit for their capacity contribution, but any given resource is going to be highly dependent on what else is going on in the system, what the load shape look like, and how that changes, how much solar is on the system, how much wind is on the system. And so you just have to be very careful extrapolating ELCC values out into the future and making assumptions about what that resource might be able to provide years in advance. And so the way I like to look at this is I really like ELCC to compensate a resource or to give credit to a resource for a given year. So, this year, this summer, we're going to compensate solar resources X for the capacity contribution they're providing given the system it is today. I get a little bit more nervous for long-term planning when you say, out in the future, resource X, Y, and Z are going to provide this capacity credit because so many of those other things can change. The third one, I've touched at this quite a bit, is modeling chronological operations is essential. Again, previous historical resource adequacy analysis just looked at the peak day and said, if I could get through the peak load hours on the peak day, chances are I could get through the rest of the year. That's dramatically changing, again, both because of renewables and storage. I think I've touched on that one quite a bit. One thing, again, that's driving towards is how we start to think about modeling weather and generator uncertainty. And I think that the best approach here is to take as many weather years as possible that we have adequate weather data for, and then run each of those chronologically across many Monte Carlo samples of different outage draws. And so you can see this is a makeup of a 250 case matrix where you have each weather year evaluated across 12 different random outage draws. And so you can see in this example, it'd be 252, but ideally you do this across thousands of simulations. And essentially what you would get is, if you ran 1,000 simulations hourly for an entire year across many weather years, you're looking across 8.8 million hours of grid simulation. And fundamentally, again, I know resource adequacy modeling can seem complex at times, but fundamentally all you're doing in resource adequacy analysis is running hundreds or thousands of different samples of different combinations of weather and outage draws and taking an average or looking at how many times you are unable to serve load. This is an example out of some work we did in Hawaii. We looked at daily solar output across 21 years of historical, again, simulated weather data going back to 1998. And you can see there are times we looked at a rolling 3-day average of solar output, and we're specifically interested in how many times or how bad could you have 3 days in a row of really low solar output. And I flagged a few big outliers here. These are kind of known weather events that happened in Hawaii and just highlighted them here. So there are times when you have 3 days in a row of really low solar production, and then what happens there. So I think this is kind of driving where we need to start thinking about weather in our resource adequacy analysis. I think the two limitations here are what happens if you don't have that much data. There's solar data, it tends to be easier to come by than wind data and load data. The second is how do you ensure that all that data is correlated and you're picking up on the right weather trends? And then lastly, with a changing climate, is it fair to use 21 years of historical weather data to project out into the future? Number 4, load participation fundamentally changes the resource adequacy construct. I touched on this one before, just the fact that we have now so many tools in our toolkit to approach resource adequacy, not just from the generation side, but also storage, demand response, electric vehicles, rate design, all sorts of controllable or just controllable loads, or just loads that are price responsive and other passive controls. are a huge part of this mix. I think where we as an industry need to sharpen our pencils is we should be modeling those resources with the same level of input and precision that we have on generation resources. So how often will it be unavailable? How much uncertainty is there in the availability of those resources? Are there scheduling constraints? Are there fuel constraints? I think that's where we need to sharpen the pencils. Number 5 is neighboring grids and transmission are a key part of the RA challenge. Michael touched on this a lot, so I won't go into too much more on this other than transmission can be a capacity resource. So again, I wanted to move away from this concept of resource adequacy being, do we have enough generation to serve the load? And transition that to, do we have enough resources? Transmission being one of those resources. And this is a snapshot of the MISO PJM seam. So it's LMPs. The bright areas are very high LMPs. The cooler areas are low LMPs. And this is during that February event when there was rolling blackouts occurring across Texas and Entergy and parts of MISO and SPP. You can see prices very low or even negative in parts of PJM. And so where you had extreme cold events in the middle of the country, very mild or normal weather in the eastern and western parts of the country. And had there been more transmission and ability to lean on neighboring systems, I think those events would have been a lot less severe. I think that's one reason why you saw 4 days of cascading blackouts or 3 days of cascading blackouts in Texas, but MISO and SPP also having shortfall events, but much shorter because of their ability to lean on neighbors. I think in general, geographic diversity can be a very valuable asset, and it can be very cold. You could lose your wind and solar in some regions, but you can't lose it all in all regions simultaneously. And lastly, reliability criterion should not be arbitrary, but transparent and economic. And I think this, as a regulator, as a policymaker in this space, really critical. As Michael said, reliability doesn't come free. And really that 1 day in 10-year metric is simply a line in the sand. And I think we fall victim to this, say we are going to build to 1 day in 10 years, regardless of the cost. And I think what's important here is to know what that reliability criterion is costing you. So what if it was 1 day in 15 years and you had a little bit more reliable system? Is it maybe it's worth building a little bit more? If you had 1 day in 5 years and had less reliability, how much did that save you? It could be dramatic. And so I think just not necessarily changing the reliability criterion, but knowing what that reliability criterion is costing you. And then lastly, with the economics discussion, I think then the question came up about resiliency versus resource adequacy and reliability. I think this is important. Obviously, as a regulator, as a policymaker, there's the bucket of money to pay for reliability is only so large. And we have to weigh that against not just resource adequacy interruption, so not having enough capacity to serve load, but also distribution outages, transmission related outages, and other pieces. And so this is an example out of Australia, shows, and I believe this is true, we'll throw ERCOT aside for a moment, but this is true really across all the systems we think about. Resource adequacy tends to be very small amount of the total interruptions that customers see, and potentially overpaying for that reliability, when if you have just a certain amount of resources to pay for reliability, maybe those funds are worth allocating to different ways. Ultimately, the customer, they don't care when their lights go out. They don't care if it was an RA disruption or a distribution change or vice versa. So I wanted to jump into some new metrics, how we can think about this differently, but first give everybody a 5-minute break, and then I'll come back and wrap up that session. I know I've tied up folks for quite a bit of time here. So 5-minute break, and we will start up at 3:46. All right, hopefully everybody had time for a quick break, and we're going to start right back up. I have 13 minutes before I pass it off to Keith, or maybe even a little bit less. So we'll hit some of the new metrics and the way I think about that shortly, and then can conclude. So I think Michael did a great job framing the metrics where we are today. So I'll save some time by not jumping into those. You can see this is a good overview provided by the New York State Reliability Council. It shows predominantly in North America, loss of load expectation is the reliability criterion of choice. You get to Europe, it tends to be a little bit more loss of load hours. Really only one region, Australia, using an expected unserved energy metric. I believe Scandinavia does as well. But loss of load expectation, counting the number of events, is kind of the predominant criterion of choice across most of North America, and the criteria being 0.1 days per year. I get a little uncomfortable with LOLE as a metric, and the reason for that is look at it as a line in the sand syndrome, where we drew a line in the sand somewhat arbitrarily, as Michael discussed earlier, with little understanding in what went into that, how we came up with that, and then come hell or high water, we're going to hit 0.1 days per year. And regardless of what those events look like, if they're really large events like ERCOT versus very small events like what we saw in California, we're going to not distinguish between those. We're just going to purely count the number of events. So that's where we are today. Again, might have been historic or useful in the historic grid where we had very similar resources and all of our shortfalls look very different. I think now that we're running into energy limitations, the over-reliance on LOLE can be troubling. I won't go into this. I thought this was helpful for the folks that wanted to look at this afterwards. But I think the takeaway here, the resource adequacy metrics can seem very daunting, but very quickly, LOLE is just counting the number of days of an expected shortfall. Loss of load is the number of events, is the loss of load events. So LOLE is often days per year. Events is number of events in a year. So it's one day could have two separate events, one in the morning, one in the evening, or you could have an event like ERCOT, that one event that lasts over 3 days. So sometimes good to distinguish between those, although oftentimes they will be the same. Loss of load hours, just counting the hours. Probability, just putting that in a percentage term. And then expected unserved energy is just the total megawatt hours of the average megawatt hours of unserved energy in a given year. And sometimes you'll see normalized expected unserved energy, or NUE, and that's just putting your unserved energy as a percentage of load, so that if your load's growing or declining, you can keep a similar resource adequacy, or you're trying to compare two regions, you can use a common metric there, a normalized metric. I went over this slide, so I won't go over that one again, but really, I think when we were starting to, on the task force with Ecig, when we were starting to think through a lot of these topics, the question was, well, do we need a new metric, or do we just need to use the existing metrics better? So do we need a change? And I think where I personally settled on this topic is we need to use the existing metrics better. And we need to use a combination of different metrics, and we have to be careful about just using the expected values. And expected values, typically all of the metrics I talked about here, all of these are expected values, are averages across hundreds or thousands of samples. You get a single average point, and that's your LOLE, or that's your LOLH. So you have to be very careful. Anytime you use averages for any type of planning, you just have to be careful about, well, what are the outlier events? And so again, I like my list. 4 recommendations for resource adequacy metrics. 1, place more emphasis on expected unserved energy. So again, I think historically people have relied on loss of load expectation, which is just counting the number of events. Expected unserved energy gives you a little bit more information. You understand more about how big the events are, and I think that's increasingly important for systems with increasing variable renewables and energy limited resources. The good news is that we don't have to use just one. We've tended to use just one in the past. But there's really no reason we can't use a combination of EUE and LOLE or other metrics as well. And so I think critical moving forward, even if you don't have a reliability criterion that uses multiple metrics, although I would say you could have an EUE criteria and an LOLE criteria of 1 day in 10 years. And you could say, I'm going to plan my system to whichever one of those occurs first. But even if you don't have multiple reliability criterion, you can use a suite of metrics and you can use it to inform decisions. So even if the criteria is 1 day in 10 years, you can say, I'm going to keep an eye on EUE or I'm going to keep an eye on LOLH because I want to see if that trends. Right now, maybe they're very correlated and they're close to each other. But in the future, as the resource mix changes, make sure you keep an eye on multiple metrics. The third one is move beyond expected values and consider the tail events. So like I said before, all of those resource adequacy metrics, they're just telling you the average shortfall over all of your samples. You're not seeing what are those worst case events, what do those look like? So if you go back to that scatter diagram that had the dots of each of the outages, what do those events in the far right corner mean that say they're very long events, very large? What's driving those shortfalls? So if you think of the ERCOT example, that one, while it's one event and it's not necessarily changing your LOLE metric much, catastrophic failure. So what can we do when we're doing this analysis? That event might have gotten lost in some of the other shortfalls. So I think the extent we can look in those tail events is going to be important. And lastly, characterize size, frequency, duration, and timing of the shortfall events themselves. So if you take anything out of the metrics discussion and all of the different acronyms and everything, try to come back to this list and say, and really my favorite, probably characterizing the size, frequency, duration, and timing of the shortfall events. So when an event occurs, know how big it is, how long it occurs for, when it occurs, and really the reason for that is it could become very clear what the appropriate mitigation is. So I'll just use some examples. Again, running out of time. I think this is a table showing comparing and contrasting the different kind of event characteristics between the California and Texas event. And you can see on a loss of load event and a loss of load LOLE basis on days, the events weren't that different. But when you start to tie in EUE, when you start to tie in the maximum shortfall, obviously very, very different events. And so important to keep track of all of these. And lastly, I'll kind of summarize with this last chart here on characterizing the size, frequency, duration, and timing of events. So this chart is showing cumulative probability distribution curves from an analysis we did in Hawaii. We looked at across many different scenarios and said, when there's an event, how big is the event or how long did it last? So here you can see 90% of all events are 4 hours or less, regardless really of the scenario evaluated. 90% were 120 megawatts, or sorry, 110 megawatts or less, and 90% were 240 megawatt hours or less. And so if you look at not just the average values of these events, but look at them, look at all of them and start to characterize them, you can start to see, well, maybe I don't need a resource that's going to be online, 30 hours or quote unquote a firm resource. Maybe I can get a lot of value out of something that's 3 hours or less. And I think when you start to look at this in that context, you really start to think about reliability and resource adequacy differently. Another way to look at that is a matrix here where I'm showing all the loss of load hours that occurred, how big were they, both in the maximum size and the amount of energy that was shed. And so you can see that 70% of events would have been covered in this context by a 60 megawatt resource that lasted 2 hours, 85% 100 megawatt resource that lasts 2 hours. And so I think that's critical when you start to say what mitigation is right. And so if I could kind of convey any last finding for the folks on the phone is when you're thinking about resource adequacy, be very careful about not just picking resources blindly until you hit that 1 day in 10 years, but really start to understand what the events look like, when they're occurring, how big are they, and say, like going back to Michael's example, the energy first planning, figure out the resource mix that makes sense for the energy and say, what do I need to make sure this system is reliable, and what's the best way to fit that need? And so with that, running out of time, I knew we wouldn't get through all of that, but wanted to provide the slides. So please reach out if you have any questions on the slides. Again, thank you to Ecig and the